At over 72 meters high, the Qutb Minar is one of the tallest stone masonry towers in the world. Built from red sandstone and marble, it stands as a primary example of early Indo-Islamic architecture. The tower is located in Delhi, India, a region the Indian Seismic Code places in Zone 4. This indicates a high risk of severe seismic intensity. While earthquakes with a magnitude of 5 to 6 are frequent, the area occasionally experiences massive events reaching magnitudes between 7.5 and 8. The minaret has survived since 1368, yet it has required continuous restoration to repair damage caused by near and far seismic activity. Preserving such massive ancient masonry from inevitable modern earthquakes requires a precise and resource-intensive structural evaluation. Accurately assessing heritage structures is difficult. Modeling the nonlinear mechanical behavior of ancient masonry in 3 dimensions requires massive computational power that is rarely available. To manage this complexity, engineers often rely on a nonlinear static analysis, commonly referred to as a pushover analysis. This method simplifies the problem by applying a monotonically increasing lateral load to simulate earthquake forces. When applied to the Qutb Minar, the static model predicts that the foundation is the structure's most vulnerable point. However, the historical record of the tower contradicts this prediction. Centuries of documented earthquake damage have occurred exclusively at the very top of the structure. When a standard engineering model fails to predict historical ground truth, we have to look deeper into the specific structural anatomy driving the failure. The Qutb Minar is a complex hollow assembly. Its seismic behavior is a function of its composite construction. The primary load-bearing system is an external shell of 3-leaf masonry. This consists of an outer veneer, an inner veneer, and a central layer of rubble infill. Inside this shell lies a central cylindrical core constructed from Delhi quartzite stone. These two systems are tied together by a spiral staircase and 27 stone lintel bracings, which structurally unify the core and the shell. This interconnected multi-material anatomy creates complex pathways for energy dissipation. These are details that a simple solid column model cannot capture. The tower's macrogeometry is aggressive, tapering from 7 meters to just 3.13 meters at the top. Each of the 5 stories features distinct structural changes, including varying flutes and balconies. Diffuse ventilation openings are distributed across the lower levels. At the 2nd and 3rd levels, these openings reduce the structural cross-section of the masonry by nearly 50%. This sudden loss of area, combined with the extreme taper, creates severe stiffness degradation at higher elevations, a variable that complicates static analysis. Revisiting the pushover analysis reveals its mathematical blind spot when dealing with such highly tapered structures. The static test applies lateral forces based on the structure's fundamental mode of vibration, the simple primary side-to-side sway of the entire tower. In this single bending arc, the 72-meter height acts as a lever, creating a massive overturning moment localized at the foundation. Because this model ignores high-frequency dynamic forces, the mathematical outcome defaults to base shear. This creates a static illusion, where the highest stress appears at the foundation, obscuring the structural realities of the tapered upper levels. A real earthquake doesn't push slowly. It injects rapid, transient ground acceleration directly into the base of the tower. Full nonlinear dynamic analysis reveals that this rapid energy transmission excites higher modes of vibration. The seismic wave travels up the massive, rigid lower stories and collides with the stiffness-degraded upper section. The combination of low mass and degraded stiffness at the top leads to localized, high-frequency whipping effects. Dynamic analysis shows that higher modes of vibration override base shear in highly tapered masonry, turning the upper levels into the structure's critical failure points. The output of the dynamic simulation aligns precisely with the historical record gathered during the background assessment. Damage in 1326 and 1368 was localized to the upper stories, eventually requiring the original 4th story to be replaced by 2 new ones. During the 1803 earthquake, the seismic waves threw the topmost cupola to the ground, leaving behind the replacement chhatri that now stands in the gardens. This structural wreckage matches the dynamic simulation, illustrating that the top of the tower acts as a sacrificial zone during major seismic events. The discrepancy between static and dynamic behaviors is a warning for those assessing ancient masonry. Pushover analysis must be used with caution on tall, irregular structures, as it can overlook critical higher mode influences. True seismic assessment requires a stepped strategy, beginning with historical background research to establish the ground truth. While simplified models provide a useful baseline, they must be tuned using data from refined dynamic simulations to overcome material uncertainties. Preserving architectural heritage requires moving past computational shortcuts. Only a comprehensive, dynamically tuned approach can accurately map the complex realities of ancient engineering.